What we're going to be doing in this video is closing out our Spring Lab to ensure that we understand the important concepts that come from it. So the first part of this guided note sheet is really just a way for you to tell me some things about the lab that you did. At this point in time, it's not super important. What's the most important thing is that you recognize that when you get your graph, you're going to get a slope, and the slope that you get for the yellow spring, I believe, was about 35, and that's fine. What's more important is this newtons per meter value, and what that means is that for this yellow spring, it takes 35 newtons of force to stretch it 1 meter. Or if it was a compressible spring, it would take 35 newtons of force to compress it 1 meter. The other value that's in there, you probably had some intercept of some force, was probably 1.8-ish newtons. And that's the amount of force that's necessary to stretch the spring at all. So you have to apply beyond some force to get it to stretch. That force is something called a loading force. For the purposes of our discussions, though, we're going to assume that all the springs that we deal with are ideal springs, and an ideal spring has a loading force of 0. However, what you found in your mathematical model that you derived is something called Hooke's law. The general form of this equation is really something that looks like this. The force of the spring is equal to negative k times the displacement. Now, there's a lot of things here. First off, F sub s is the force from the spring. That's important to remember, that we're looking at the force from the spring, not some force that's being applied to it. The k value is something called a spring constant, and it's a measure of how much force is necessary to stretch the spring, and it's measured in newtons per meter. So for this yellow spring, our spring constant would be 35 newtons per meter. And our displacement, or our x, is the displacement from equilibrium. So how far beyond its natural length is this spring stretched or compressed? And this is measured in meters. Now, there's also this negative sign here, which is a little weird. You wouldn't expect to see a negative sign there. What that negative sign means is that the spring force that's acting on an object and how much the spring has been displaced are in opposite directions. And we would expect that. If I pull a block outward on a spring and then I release it, I would expect the spring to pull it back, because a spring is something called a restoring force. So this implies a restoring force. That's not super necessary right now. It will become more necessary later on, but I do want to make sure you are aware of it. On your AP equation sheet, at this point in time, they're ignoring that. So you're simply looking at the absolute value, or the magnitude of the spring force can be found by k times x. Okay. So let's draw a sketch of an ideal spring. And with an ideal spring with force and displacement, what you're going to get then is there's no loading force, so it starts at 0, and then you get some slope, some linear function. And the slope of this line, remember, is your k value, or your spring constant. Now, if we look at the axes, we can determine the amount of work done on this system because we have a force displacement graph. And if you want to find the work done from a force displacement graph, you're simply looking at the area under the graph. So if I were to calculate the area under this graph, I would be able to determine the amount of work that was done on this spring for that displacement. By determining the amount of work done on this system, we can determine the amount of energy in the system. Remember, work is done to change the energy of the system. However, we're not adding a kinetic energy. Instead, this time we're adding a potential energy, which is also sometimes called a stored energy, which means that I do some work on it, and then if I change something, then it's going to do something else. That energy is going to be released. If I pull a spring out and then I let go, I release it, then it is going to release that energy. That's a stored energy. This type of energy is known as an elastic potential energy. And we can find that elastic potential energy by finding the amount of work done on this graph. Oh, okay. Well, if I look here, I would say, well, that's a triangle. So I could say that the amount of work done is, first off, my change in energy. But the amount of work done is 1/2 times the force times x. But I know that my force is given by k times x, just magnitude-wise. So then that means the work done on this is 1/2 times kx times x. Or the work done is 1/2 kx squared. So the amount of work that I do on this spring gives it an energy which is equivalent to 1/2 times the spring constant times the displacement squared. So when I do that, now a spring has a potential energy, and the amount of potential energy it has is given by this equation. So our potential energy U sub S for a spring is equal to 1/2 kx squared. Okay, so now we have two new equations, one for a spring force, remember we only really look at magnitude, and the other for a spring elastic potential energy. Okay, and this is true, and the reason we do this instead of just F times X is because this is not a constant force, and if I don't have a constant force, then I can't just do FD cosine theta. If I have a changing force, I have to find the area under the graph. Okay, let's keep moving forward then. And what we find here is to possess a stored energy means that the system must be able to do work on its surroundings. Let's think about this. If you stretched a spring and then released it, what would happen? We just talked about that. Would the system be able to do work on the surroundings? Would energy transfer? I think the answer to that is yes. So you have a definition for work already. You have a definition for kinetic energy already. What I'm going to add here is a definition for an elastic potential energy. So elastic potential energy, by definition, this is energy stored in a compressed, which means it would be one of the springs that you push together, apply force to push it together, or extended spring. And the units of it, since it's an energy, are joules. And the symbol, as we said, was US. Okay, so we have all that information there. So let's take a look at a practice example. And notice here that I have a graph. And I'm using this graph to solve. When spring 1 is stretched 3 meters, how much energy is stored? So I'm looking at two springs. In this case, I have spring 1, which is given by my squares, and I have force and displacement. Well, with that being the case, if I stretch 3 meters, then that means that I end up 1, 2 right here. If I want to know how much energy there is, then I need to find the area under this graph. So it looks like it's about there, about 15. So I get 1/2 times 15, which is my height. This is what I'm looking at, times 3, which is my run, or my base, I suppose, and I get 22.5 joules. Great. Okay. And then how far would you have to stretch spring 2 in order to store 24 joules of elastic potential energy? So I want to store 24 joules of elastic potential energy. So in this case, it may be easier to use the equation 1/2 kx squared, because it's going to be harder to try and figure out where exactly I get 24 from this equation. So with that being the case, I know that my elastic potential energy is 24 joules, and I'm trying to find the displacement, which means I need to find the k value. Well, that's easy enough, because the k value is simply the slope of the line. So pick 2 points on this line. I'm going to pick, I don't know, this one maybe. that one, and I'll pick this one, this point here. So it looks like my rise is 16 newtons minus 4 newtons divided by 2 meters minus a half a meter. So I get 12 newtons per 1.5 meters, or 8 newtons per meter. So now I have a K value of 8 newtons per meter. With that, I can solve this problem. So I'm looking for X, so 2 times the elastic potential energy divided by K square rooted will tell me my X value. So X is the square root of 2 times 24 divided by 8. And in this case, I get the square root of 6, which is 2.45 meters. Okay, keep working through the practice examples on the next page, and best of luck.